Next is nuclear magnetic resonance or NMR. In NMR, we are studying about the interaction of radio frequency electromagnetic radiation with the nuclei of molecule that is placed in a strong magnetic field. Please remember that the energy of the electromagnetic radiation in NMR lies in the radio frequency range. If we consider ESR, we have studied the interaction of microwave radiation with electron that is placed in a magnetic field. Whereas in nuclear magnetic resonance, we are studying about the interaction of radio frequency electromagnetic radiation with the nuclei of molecule that is placed in a strong magnetic field. Now, before going to nuclear magnetic resonance, let us revise some basic concept in ESR. If you consider an electron, it has a spin vector. The magnitude of the spin angular momentum, yes, we have seen this is equal to square root of s into s plus 1 h bar. Also, ms, the magnetic spin quantum number, quantizes the set component of spin vector. This is equal to ms h bar. And also the magnetic dipole moment due to spin motion mu equal to minus gb minus g mu b by h bar into s, where the negative sign is due to the fact that the electronic charge is negative, where mu b is the Bohr magneton, that is Eh bar by 2m. We have seen all those things, and this is for electron. Now you consider, now let us come back to the nuclear magnetic resonance. Suppose that nucleus has a spin, then similar to this, you can define nuclear spin angular momentum. Here it is the magnitude of s. This is equal to s. If you consider a nucleus having some spin, then you can define nuclear spin angular momentum in the same way. You can define nuclear spin angular moment, that is for nucleus we can define I, this is equal to square root of I into I plus 1 h bar, where I is the nuclear spin quantum number. Nuclear spin quantum number. Similarly, here also we have we can define magnetic spin quantum number associated with the nuclear spin, and we can say that it quantizes the set component of I. So Iz equal to some mi into h bar, where mi is the magnetic quantum number associated with the spin, and in the case of electron we have mu, that is the magnetic dipole moment due to orbital motion. In this case we can define it like this: mu equal to some gn mu n I by h bar. Here if you see, the sign is positive because nucleus has a positive charge, whereas in the case of electron has a negative charge, so there is a negative sign. but here it is positive. The expression is same, but the parameters are different. It is Gn, and instead of Bohr magneton we have mu n, where we can define mu n. This is equal to nuclear magneton. This is nothing but nuclear magneton. The value is equal to EH bar by 2 times mass of proton. Whereas for Bohr magneton, this is Bohr magneton for electron. This is EH bar by 2m, where m is the mass of electron, whereas nuclear magneton is EH bar by 2mp, where mp is the mass of proton. Okay. And Gn is the nuclear G factor, etc. Now consider your nucleus. Now consider that your nucleus is placed in an external magnetic field. Now before magnetic field, it's an external magnetic field, right? Suppose nucleus. Suppose a nucleus is placed in external magnetic field. External field B0 in the Z direction. Now we can write this in this way. This is your Z direction. In the same Z direction the magnetic field is applied, and suppose this is your the nuclear spin vector I, and if this is theta and this is the Z component Iz, this is Iz, Z component of your spin vector. Now we know that I, what is I? I is equal to root of I into I plus 1 H bar, and Iz, this is equal to Mi into H bar, so that you have cos theta equal to Iz by I. This is equal to Mi divided by square root of I into I plus 1. Now what about the interaction energy? When you have a nucleus that is placed in an external magnetic field, what is the interaction energy? The interaction energy is again given by E equal to minus mu dot B0. This is equal to minus mu B0 cos theta. Now let it be your equation number 1. Let it be your equation number 2, and suppose that your equation number 3. Now 1 and 2 in 3 implies E equal to, what is mu? mu equal to Gn mu n I by h bar, that is minus Gn mu n I by h bar, that is mu, then B0. What is cos theta? Cos theta is nothing but mi divided by square root of I into I plus 1. Now we can rearrange like this, minus Gn again mu n, I is nothing but root of I into I plus 1 h bar divided by h bar, then B0, then mi by square root of I into I plus 1, and this implies E equal to minus Gn mu n B0 sorry, some error, and this is Gn then mu n B0 mi. This is the expression for interaction energy, the interaction energy of a nucleus that is placed in an external magnetic field. We can say that E equal to minus Gn mu n B0 mi. Interaction energy. Now for a nucleus, of spin I, for a nucleus of spin I, then mi can have 2i plus 1 values from minus I to I. Now for I equal to half, consider a nucleus with a spin half, then mi equal to plus half and minus half, because the value of mi varies from minus 1 by 2 to plus 1 by 2. So that you can define two quantities, that is depending upon the value of mi, you consider a nucleus having spin half, then the value of nuclear magnetic quantum number mi equal to plus half and minus half. So you can define E half corresponding to mi equal to plus half. This is equal to minus Gn mu n B0 and E minus half. This is equal to Gn mu n and B0. That is, in the presence of a magnetic field B0, your initial energy level E is split up into E half and E minus half. Now, how can you draw this diagram? We can draw like this. This is in the absence of the field. When the field is applied, your level will split up into two. Now this corresponding to mi equal to minus half, and this corresponding to mi equal to half. Always write the upper energy level as positive energy. Here the positive energy value is E minus half, that corresponding to mi minus half. So this is E minus half. This is equal to Gn mu n B0, and this is E half. This is equal to minus Gn mu n B0. That is the presence of a magnetic field, that is B not equal to 0, make the energy level split. The presence of the magnetic field cause the energy level to split, corresponding to the values of mi equal to plus half and minus half. Now in this particular situation, suppose the molecule absorb. In this particular situation, suppose the molecule absorb an electromagnetic radiation h nu, where please remember that this is radio frequency electromagnetic radiation. This is radio frequency electromagnetic radiation is absorbed by the molecule. Then there is a transition between this magnetic energy level. Already our energy levels are split due to the presence of a magnetic field. So in that situation, if the molecule absorb radio frequency electromagnetic radiation or RF frequency, then there will be a transition between mi equal to half to mi equal to minus half. Now what is the minimum energy required for this transition? The minimum energy that is required is the difference between the upper level and a lower level. This is equal to E minus half minus E half. This is equal to here something is missing. Here it is divided by because the value of mi equal to plus half and minus half, here it is divided by 2, and here it is also divided by 2. Here it is again this divided by 2, also divided by 2, and the result is Gn mu n B0 by 2 minus Gn mu n B0 by 2. This is equal to Gn mu n B0. That is, this condition is called the resonance condition in NMR. That is, when h nu equal to Gn mu n B0, there is a transition between the magnetic energy levels of a nucleus that is placed in an external magnetic field. Here the frequency of radiation that lies in the radio frequency region of electromagnetic spectrum, and this condition, that is h nu this is equal to Gn mu n B0 is called resonance condition. Resonance condition in NMR.